Good evening. Welcome to Space Oddities. Thank you for joining us. If you're new here, you are indeed very welcome. And if you're not new here, you are still very welcome. So we've got quite a bit on the program tonight to get through. So without more ado, let's go first of all to Roger. Roger, what's up?
Oh, the usual stuff, but we'll get to that in a minute. So let's.
Good evening. Welcome to Space Oddities. Thank you for joining us. If you're new here, you are indeed very welcome.
Ooh.
And if you're...
Ooh, right. Okay, here we go then. There we go. Right, so here we go for our weekly roundup of this week's events for the 15th to the 21st of August. As usual, we've got the third quarter coming up later in the week for you lunatics. And this was what was up in the night sky last night during the wee hours of last night. So we're gradually getting back to the last quarter. And while I was out observing the moon, I also did Jupiter, which is
oh, that's great.
Not coming out too bad. Still a long way from Damien Peach, but there we go. Just got the great red spot disappearing round the limb there, unfortunately, but not too bad. And then there was Saturn here, and that was at its opposition just a couple of nights back. And as you can see from the ring here, you've got the Sealinger effect, where the ice crystals are reflecting the light directly back to Earth as it goes around at the opposition time. So brightens up considerably during that brief spell. So quite a good spectacle to see when you can get out to see it at night. Although it is up there late at night, so it's becoming more of an evening opportunity, especially for Jupiter and Mars as it's arriving through Taurus and onwards towards the Pleiades. We're just coming past the peak of the Perseids, and there's a couple of meteors which I managed to get.
Oh, well done.
Not as many as Mary McIntyre does on her meteor cams, but nevertheless, amazing. I did get a few, so that didn't turn out too badly. Okay, so for the week ahead, we've still got Saturn, Jupiter, and Mars in the night sky, and if you're up a bit later with Mars, you will start to see the winter constellations of Taurus coming up through. And as I said previously, it will be getting nearer to the Pleiades later on, and will retrograde in Taurus later in the year. So something to watch out for there as well. So as we gradually work our way through, the moon gradually goes through between Mars and the Pleiades as well on Saturday. Right, and if you have anyone in the southern hemisphere, we've got the same planets a wee bit higher up in the night sky, and also Orion up quite nicely up in the night sky. So that's rather nice for them. So we'll have that soon enough when we get the next few months. Okay, that's a very brief roundup of what I've got to show you.
Thank you very much, Roger. Fantastic stuff. Okay, well, we'll move swiftly on then. Rachel, do we have any viewers gallery for this week?
We do. Fantastic. I was just having a quick look at it when you answered, so let me just put it up for you. Right, hang on. Let's go. See how this works. Okay. So yeah, we've had quite another nice collection in for this week. So I'll start off with Kev. He's not sent in a son. We've got Kev's Solar Nebula. I haven't put where it is, but I believe it's in Cassiopeia. IC 1848, I think. And he did add some words, but I think his words were, there are no words, it's a nebula. So here we go.
Oh, wow. Well done, Kevin.
That's good.
It's a lovely Solar Nebula in a bicolor palette.
That's beautiful colors. Look at that.
It is, yeah, and I think it's quite a starry area as well. So the star control is really nice on this image as well, and still a little bit of star color too, which is always nice because I know I can sometimes go a bit far and take all the color out, but it's very nice. Thank you, Kev.
Yeah, there's some nice definition in the bottom right hand.
Yeah, that's beautiful definition.
Well, yeah, it's really 3D, isn't it? You get a real sense of depth with it.
And Kevin will actually be joining us here in just a few minutes to talk about his astrophotography. So stick around because we're looking forward very much to talking to Kevin, who's been a regular contributor to Space Oddities and a regular listener to Astro Radio as well. So
another regular as well of both shows. Lee was an avid listener of Astro Radio as well, and he's in Cornwall. And he sent in a lovely picture of Noctilucent St. Clouds, and he said they would have looked better without the spaghetti junction of wires outside my flat, but it was a spur of the moment thing when I opened my blinds to get ready for work. No chance to get anywhere quick, so he took what he could, and it's his first experience of seeing Noctilucent St. Clouds as well, so he was really excited for this. And there you go.
Oh, he did get them, didn't he?
And
Wow.
I quite like the lines. I think it adds something
Yeah, it
to
does,
it.
doesn't it?
Yeah.
Which is really lovely and a really nice display actually, because I've not seen many this summer. So very nicely.
Beautiful. Well done, Lee. That's fantastic. Lovely.
And then we've got Roger in hot with the Leo Triplet. So Roger's details are there on the screen, and obviously Leo Triplets within Leo. And here we go.
Oh, that's nice.
Wow. Well done, Roger.
Yeah, I really like that. I really like the is it the hamburger? Did they call it the hamburger galaxy? Or am I making
Yes,
that
one
up?
on the left.
No, it is the hamburger, yeah.
It's really nice. And I always think the one on the top right one, it looks like Captain America's shield. Because I feel like I feel like there's like a center and almost a star shape. Just slightly going into it. But yes, lovely. Good job, Roger.
Yeah, I managed to get the arms on the bottom one quite well.
Yeah, the definition there is fantastic.
It is, isn't it? Very
And
good.
then this is again another regular watcher, Andy, and he's done the Crescent Nebula. And this, I've said this before, so we've just imaged it ourselves. I used to hate this nebula. I said it was really ugly, and it was just one I was completely not interested in until I saw Andy's, and that completely changed my mind because I think this is absolutely stunning. And I believe it got photo of the month in either Astronomy Now or Sky at Night.
Oh, wow.
My goodness.
And
That's amazing.
yeah, I think even just to say how closely in it's cropped as well, the detail on it and those different shades.
Yeah.
And the blue like envelopment of it is just wow.
It's that blue particularly that looks wonderful around the edges.
Ah, that's amazing.
He did. He changed my mind with that one. So thank you again, Andy. I think that was all I chose for this week. So I kept it nice and short and sweet.
Oh, right.
Sorry, Kev's just joined. Do you want to pop back and see if he wants to talk about his?
Well, he's here.
Yeah, if you, I can put it back on the screen if you want. If Kev's ready to talk about it.
He's just connecting to audio.
You do it, and I will whiz through. I'll put Kev's up for him.
Looks like he succeeded. There we are. Good evening, Kevin.
Good evening, everybody. Good to see you.
How are you?
Kevin.
Yeah, I'm good, thank you.
Nice to meet you at last.
Indeed, yeah. You may have seen me on Dave Eagle's Zoom, perhaps. I don't know if you tuned into that.
Right. No, I haven't.
Yeah.
Well, we've just been looking at your latest image, or one of your images that you've sent, Kevin.
Yeah, there's the soul. Yeah, that was quite an old one, I think, now. But
Really?
yeah, I haven't been doing much deep sky lately.
It's a beautiful image. You want to tell us anything about it? Because the definition you've got there is absolutely incredible.
Yeah, I think Rachel summed it up. It's a nebula.
Yeah.
I think I did about 6 or 7 versions of that. Some of them in a sort of false Hubble palette, some in different, different combinations of reds and pinks. This one is slightly more peachy, which I know is something that Rachel likes to do herself. So I thought I might stand a chance of getting it shown if I stuck a bit of peach in there. But other than that, it follows fairly standard, process flow. I separated the stars from the nebula using StarNet, so it could process both separately. I think there's a mild star reduction in there as well. That's about it. I was actually going to go for the HARS, but it's a bit too big for the sensor I'm using, so I went for the solar instead. So the HART, I think, needs a mosaic to do that justice, really.
Yeah. Fantastic. And of course, we know you, primarily for your solar photography.
Yeah, I think I've been interested in imaging since probably the 80s or so. But back in those dark days, of course, it was all slide film and black and white, conventional film. I used to do my own hypersensitization of Kodak Technical Pan 2415.
This before I was born.
Sorry?
Was this before I was born, Kev?
This was before you were born. By a year or two only, though. And then my own developing and so on. And that was super fun and really, really difficult to get anything decent out of it. And I'm not sure I succeeded. But since digital, of course, everything's become, in some respects, a lot easier. But the challenges are new. There's different challenges these days. So once digital came along, sorry, I forgot to say my old interest in the old film days was mainly star fields, but then also lunar and planetary, because they were bright. You didn't need a particularly good guided telescope to take deep sky photos. In those days, I think doing long exposure photography was quite difficult and almost unheard of, I think, in the amateur community. But when digital came along, of course, that opened up a whole new sphere of possibilities. So whilst I would still always class myself as a lunar and planetary man. Since I've got into solar photography about a year and a half ago, it's such a comfortable thing to do. You can sit there in your t-shirt, or lately with not a lot on at all because it's so hot, under a blanket to try and see the laptop screen. But it's such good fun, and because it changes every single day, which is one thing I love about the sun. You never know what's going to crop up. But I am getting more and more into deep sky now. I've got some, a proper one-shot color camera. And a little bit more kit to help me along that road. So I am getting into to deep sky, and I've been doing some imaging this week of nebulae and the like, battling the moonlight, of course, which is not ideal. But at least I'm starting to get back in there again, which is great fun. So it's always something new. Always something new.
So would you say that solar photography is your favourite, though? Is it something that you get the most pleasure out of?
I wouldn't say so. If anything, I think planetary gives me the most satisfaction because it's very, very difficult to get really good quality end results. The techniques for planetary, as those who do that sort of photography will know, are very similar to solar. You're essentially doing lucky imaging, where you're taking an AVI or a SIR video file of a few thousand frames, and then you're hoping that some of those will be really sharp, and then you're using software to select out the sharp frames, which is where the lucky imaging name comes from, and then you stack those and then process them as you would any image, and that's the same for solar and for planetary. The difference with solar, of course, is that you need special kit for if you want to do hydrogen alpha. You need a bit of kit that will allow you to see hydrogen alpha. You can't just use a hydrogen alpha filter like you would do for deep sky. You need something like a proper Lund solar scope or a Daystar quark, which is what I use, which are not quite as good, but they're an awful lot less expensive. And they take a bit of getting used to, getting the settings of those sort of optimized. But yeah, it's great fun. It's great fun.
Fantastic. Anybody have any questions for Kevin? No?
I was wondering in relation to the colouring of the Sol Nebula. Do you know whether is it a reflection nebula or an emission nebula? Simply because usually, if it's an emission nebula, they tend to be sort of naturally red, I think, in the sky. Do you happen to know, Kevin?
I think it is an emission one. Rachel probably would know better than I, but I don't think there's any reflection nebulosity in the Sol.
No, I don't think it is an emission nebula.
Yeah.
So it's kind of energized gas that's actually giving off radiation. Yeah, thank you.
I think we all take. I mean, it's well known. It's not a secret or anything, but everybody knows that colours in astrophotography tend to be manipulated. For different effects. Some of it is purely an artistic look. Other times it's to try and emphasize different wavelengths in slightly different colours to bring out features that you wouldn't see if it was a more monochromatic type image. But I think everybody knows that. It's not trying to deceive the viewer. But I think for the Sol, the ones I've taken, I know Rachel's taken some lovely ones also, shown in the Hubble palette are spectacular, the blues and the golds. But its natural colour, as you say, Steve, is more shades of red.
Yeah, I'm not knocking the colour rendition. It was an absolutely wonderful photograph.
No, I mean, everybody has their preferences. There's no right or wrong. I like them all. As I say, I think I've processed that Sol probably 7 or 8 times in using different colour palettes, and it all depends which colour I'm after on a particular day, really.
I love the right sort of centre lower was a really black, almost like what I would have called a Bok globule. It probably isn't, but it was a really contrasty black area amongst the peach. Really good.
No, you know it better than I do. I shall have to have a close look at that.
Well, I'm just picking up from your photo. It was wonderful.
Thank you. That's very kind.
So obviously, Kevin, you've had an interest in astronomy for a very long time. What's your earliest memory and what got you into astronomy? Was it something at school or?
Yes and no. I think my earliest memory, and this, I always retell this because it's such a vivid memory. As a youngster, probably 9 or 10 years old, me and some mates were walking back from the village fish and chip shop with sort of fish and chips in hand, eating them. And a hugely bright meteor flew right across the sky in front of us, and I dropped my fish and chips all over the floor. So that's my earliest recollection. But in terms of getting into it a bit more seriously, if that's the right word, my dad worked in the physics department of Liverpool University, and he always tried to encourage me. And I did an O-level physics project at school where we could choose a subject. And I chose astronomy and then started to read up and so on about the different aspects of astronomy. And my dad brought me home, just happened to have lying around, some 6-inch Newtonian mirrors, which we then spent a few months between us building a telescope out of those, which was my first proper telescope, which really got me excited. And the moon particularly, so let's say that was my first love. And that was probably when I was about 12, I suppose. I was doing that, and then you go on from that. I've built lots of telescopes over the years of different types. The largest one being a 10-inch Newtonian, which was good fun. I still got it. I haven't used it for a long time now. And about 5 years ago, I built an observatory, a roll-off observatory, which was the best thing I ever did. Anybody who's contemplating building one of these things, don't hesitate. It will transform your observing and your imaging. So great fun.
Okay, then the most important question out of that story is, did you pick the chips up?
I can't remember that bit. As a youngster growing up in the suburbs of Liverpool, probably it is,
Yeah. I mean, and as you said, you're of the old film school, and there were many techniques and all that. But of course, you need to talk to Andy because he remembers glass plates.
So, I don't go quite that far back.
Well, at least my astronomy books aren't written in Latin, does.
Greek. What you on about? Greek.
Unfortunately, I do, because when I did my astronomy O level back in the day, there was a neighbour with all the gear that was needed, but he used glass plates to take the photos. Would you believe?
It's a bit of a lost art, isn't it? It really is.
Yeah, it's a great shame.
Yeah.
I think some diehards still do it. I think you occasionally see references to people doing their own film imaging.
Kevin,
Yeah, 'cause
I don't know if you saw our show last week on 2 weeks ago, where we talked about our trip to Stellafane Telescope
Indeed.
Makers Conference, and Dava Sobel gave the keynote talk, and she gave it about her book, The Glass Universe, which is all about women and their discoveries using glass plates.
Yeah, absolutely.
And of course, these glass plates are now the ones that they've opened up these libraries of these glass plates and all that, and they're using them again because now what we know, there's probably things on there that were missed at the time, and they're digitizing them and going through them again and finding more and more discoveries. Which is really fantastic. So never throw anything away.
No, indeed.
So,
the Stellafane thing, Lou, I really enjoyed that presentation that you did. I used to follow the Stellafane convention in Sky and Telescope back in the day. Every year I used to love it because I was interested in making telescopes. I used to love all the different designs and so on. It really inspired me to do different types of designs, which was great.
It is amazing what these people have produced, not just technologically, but visually. Some of the telescopes were works of art.
Yeah, I hasten to add that they were far better than anything I ever built, but the inspiration was there.
It's always nice to see people making, not just functional things, but artistic works as well, isn't it? The thought that these people put into it is just crazy, and the craft of it. Well, fantastic. Well, Kevin, listen, we hope you're going to continue to send us some wonderful images in for our gallery each week, because A, they're fantastic images, and B, it's really much appreciated. So you're welcome to hang around for the rest of the program, which is another 35 minutes, or if not, you can sidle off and do something else. But you're welcome, of course, you're welcome to stay.
Well, I'll be watching it anyway, so I may as well stay online. Just in case.
Okay, fine.
Andy, just as a quick one, before Kev finishes, there's Space Barnes Productions. It's just popped in a question. It says, do you get much higher resolution with glass plates more than full frame? So does anybody know the answer to that?
Do you get more? Do you get higher resolution with glass plates?
Well, the thing is, till relatively recently, those big double-page adverts you saw in lifestyle magazines showing cars and things like that, they were still shot with plate cameras because they could get a much higher resolution than they could with digital cameras. The biggest pixel count I think you'll find on commercially available cameras for professionals is about 150 megapixels. How that compares to a full plate camera, I don't know.
Well, it's quite high though, isn't it? 150 megapixels.
Yeah,
absolutely. Yeah. Okay, right. Well, thank you for that question. We don't definitively know the answer, I don't think. But we can find out. We'll let you know.
I can see homework coming on.
Yes, take that as your homework, Daz.
Oh, me?
Yeah. Well, you mentioned it. Off you go. That's your homework for the week. So, by the way, Daz, your volume's a little low.
Oh, is it? Sorry. We'll sort that out.
A little. Okay, moving on then. Lou, have you got anything for us this week?
I've got two things for us. We'll just start with one though, and that is we'll continue on with our series on exoplanet detection. So let me pull something up here. There we go. Everybody see the screen?
Thank you.
We can see your slide view. Do you want to run the show?
Ah, good point. There we go.
There we go.
Okay.
That's
So we've covered quite a lot of territory in terms of how you detect exoplanets. And there are many detection techniques. pulsar timings, radial detection, transit detection, astrometry, transmission spectroscopy, and all of those have been indirect ways of detecting extrasolar planets. You don't actually see the planet. You see the atmospheric absorption lines, perhaps, of the planet, or the fact that the star is moving, but you don't see the planet. You're inferring the existence of the planet. Today, we're going to talk about direct imaging, the pictures we've actually taken of planets around other stars. And this is very difficult to do. As you might imagine, these stars are trillions of miles away. The planets are smaller. They don't give off any of their own light. They have reflected light. And so the analogy that we've been using is a car with bright halogen headlights at a mile away at night, and you put a pea or a golf ball set right next to it, and then you try to image that pea or golf ball. Very hard to do, but it has been done. This is the first image of a planet around another star. This was the 2M1207b. Remember our naming convention that the first planet you discover around a star is given the letter B, and then successive planets are C, D, E, and so on. This picture, this actually a series of pictures, was taken with the Very Large Telescope at the European Southern Observatory in Paranal, Chile. It was taken in 3 different infrared wavelengths, and of course, adaptive optics were used to account for the absorption and the kind of the tumultuous nature of the atmosphere. This picture was taken back in 2004, and it's no surprise, I think, that this the planet that was imaged here is 5 Jupiter masses in mass. Right? It's a big planet. Therefore, it has a large surface area, and it's reflecting lots of light. So that's what you would tend to find. It's orbiting at about 55 AU from its star. It's 55 times the Sun-Earth distance. And it's about 230 light years away. So this was the very first, back in 2004, image of an exoplanet. Here's another kind of time series of multiple planets around a star. These are 7 images of the star HR 8799 system. And you can see at least 3 of the planets, actually 4 if you go out to the upper right, orbiting very clearly. These images were taken from the Keck Observatory over a period of 7 years. So these are kind of 7 individual images that were kind of interpolated to get a smoother orbit. And these images were taken between 2009 and 2016. What you're seeing here are 4 super Jupiters, right? Once again, big planets, lots of surface area to reflect with. And their orbital periods are decades to centuries, so they're quite far from their star. But I just thought this was an amazing animation.
It is, it's amazing.
So I mentioned there haven't been many visual detections of exoplanets. There have been about 25 to date. This is a listing of 7 of them, I guess, 3, 4, 5, 6, 7, no, more than 7. And you can see that most of them are fairly massive, right? More massive than Jupiter. Radiuses that are larger than Jupiter, right? Again, no surprise there. And no orbital periods and so on and so on. You can see the information that's displayed there. And if you want to find out more about that, of course, you can go to the NASA Exoplanet Archive. And I always display the NASA Exoplanet Archive homepage, as well as now Eyes on Exoplanets, which I will talk about each time we get together. This is the 3D animation, interactive animation that NASA Jet Propulsion Laboratory put together of all the known exoplanets. So I will end there. That is our 6th exoplanet detection story.
And I will put those links for the Exoplanet archive and eyes.nasa.gov. I will put them in the description of the video for you viewers. So well worth investigating both those. Fantastic. So have we reached the end of the Exoplanet series then, Lou?
There's at least one more.
Oh, fantastic. Good.
That has to do with, I'll just say that has to do with using general relativity to detect exoplanets. We'll get to that next week.
Intriguing. Sounds intriguing. Okay, so let's move on. Keith, have you got anything for us this evening?
Yes, I've got another slightly unpopular, very vaguely mathematical, mind-bending thing to do.
Oh, no,
everyone's going to switch off now. But before I start, actually, the background behind me is in fact the Aurora, which was detected at around about between midnight and 1 a.m. on Monday morning last, so 7 days ago. And there's a setup at Lancaster University in the UK called Aurora Watch UK, and they got an app which you can run on phones and things, and it suddenly went berserk. The magnetometer up at Lancaster was going nuts, and so I ran outside with a camera, and the thing was I'd already got a camera out doing meteor detection, so I thought, what am I going to do? So I grabbed another camera and put a very fast lens on it, an f1.8 standard 50mm lens, and took this picture which you see behind me. The only problem is that the Nikon 50mm 1.8 lens has probably, arguably, the most horrible spherical aberration in the whole universe. And in fact, actually, if you blew the picture up behind me, the stars at the edges of the picture look like seagulls. They're so distorted. So anyway, we'll move on, and I'll just get my things started. Bear with me, folks. I just got to press the right buttons. I'm out of practice, you know, that's the problem. Right, there we go. And I'll see if I can get that started now. Yeah. I thought I'd talk tonight about solar and sidereal days. It's an interesting thing, and when I was a kid I didn't really understand it, but I think I do now. Basically, you can do a kind of thought experiment, and in fact Open University students in Britain used to actually do this experiment for real, and that is to time the transit of an object in the sky against a vertical object like a building or something of that nature. Now, if you were to watch the sun each day pass behind an upright object like one of these poles in this picture here, you won't be too surprised to know that, in fact, that 24 hours later, and you can see I've changed the date underneath, it looks pretty much exactly the same. So a solar day is 24 hours long. But if you do the same experiment with a star, and in this picture here, the little dot that's right next to that right-hand column is the star Sirius. And by the way, some of you in the background, you probably see in the background here, Orion on the upper right. If you watch Sirius disappear behind a vertical object one night, and imagine we did this next January when it would be visible at about 1 a.m. in the morning. If you then do that the following night, lo and behold, you find it's arrived 4 minutes early. That actually, instead of arriving at dead on 1 o'clock, it's actually arrived at 00:56, about 4 minutes before that. And in fact, if you think about it, that makes sense, because if that didn't happen, then we'd see the same constellations in the same direction every night. And we all know that they change. Now, what it proves to us is that, that the Earth actually spins with reference to a distant object, like a star, like Sirius, in 23 hours, 56 minutes, not 24 hours. And so if you're looking at an object in the distance, you'll find that every night it'll be 4 minutes earlier than the night before, because the Earth spins faster than 24 hours. And that's fine, but then why then is the sun appearing against this upright object every 24 hours instead of every 23 hours, 56 minutes? Well, having established the idea that the Earth goes 360 degrees, a complete rotation, in what we call a sidereal day, 23 hours, 56 minutes, the Earth must be spinning more than 360 degrees in order to put the sun back in the middle of the sky at the same time on successive days. And in fact, I'll come to those figures in a minute. But looking at the sidereal day, of course, it reminds us that these kind of devices which astronomers use, trackers of various kinds and equatorial mounts, that if they were able to spin completely round 360 degrees, they would do that in 23 hours, 56 minutes. That's how they have to be timed, so that they spin obviously in the opposite direction to the Earth's spin, so that they track the objects across the sky. Okay, so the sun then basically is not a distant object, and we're actually orbiting around the sun. And of course, as it takes 365 days to go around the sun once, that's 360 degrees. So therefore, every day we move about 1 degree around our orbit with respect to the sun. So in order to put the sun back in the middle of the sky each day, the Earth has to rotate 1 degree more than 360 degrees, about 361 degrees. By the way, I'm approximating figures, but it's pretty much the case. And that, of course, to do that extra 1 degree takes an extra 4 minutes. So we have a 24-hour day with respect to the sun, but with respect to different distant objects like stars and so on, it's 23 hours, 56 minutes. So 24 hours, the solar day, 23 hours, 56 minutes, the sidereal day. But it doesn't end there. The thing is that, in fact, when we say that the solar day is 24 hours long, what we really mean is a mean solar day, an average solar day, if you like, because it would only be the case that the days would be exactly the same length if the Earth's orbit was perfectly circular and that we traveled round the sun at the same speed all the time. But in practice, we're close to the sun in the winter, in the northern hemisphere, that is, and we're further from the sun during the summer. And so when Americans reach the 4th of July, they are, of course, celebrating International Aphelion Day, when, of course, the Earth is furthest from the sun. Anyway, in January, we are actually closest, which, by the way, reminds us, of course, that seasons are nothing to do with the Earth's distance from the sun. It's to do with the Earth's tilt. So at certain times, the Earth is speeding up as it goes from perihelion to aphelion, and at other times it's slowing down. And so the sun arrives back in the middle of the sky slightly early at certain times and slightly later at other times, depending on the Earth's motion around the sun. And so if we use a sundial, it doesn't keep perfect time because of that variation. And in fact, there is a thing called the equation of time, which is like a correction graph to enable you to set the time correctly from your sundial. So if you've got a sundial shadow there, it may not be telling you the truth. Well, it is telling you the truth in the middle of April, in the middle of June, and at the end of August, and late December. But the rest of the time, it's out by a certain amount. Now, some of you will be looking at this graph and thinking, hang on a minute, I can't really correlate that to the orbital diagram that just came on the previous page. There's another thing. Remember, I said the Earth's tilted. So the combination of tilt and the fact that the Earth has an elliptical orbit causes the solar day to vary in length according to the graph you see here. So at certain times, like in the autumn, sundials run about 15 minutes fast. And at other times, like in the late winter, early spring, it's running 15 minutes slow. So there you have it. The sidereal day is a true rotational time for the Earth, 23 hours, 56 minutes. And the solar day with respect to the sun is on average 24 hours. Thank you very much.
Thank you very much. Absolutely fascinating. I never realized that sundials could run fast or slow. That's that's a new one on me, but it makes perfect sense when you think about it.
So
yeah,
so
wonderful.
Keith, do we really know? Does anybody really know what time it is?
Yeah, well, that's true, isn't it? It's yeah. I couldn't agree with you more. And of course, in this modern age, we don't have to worry what sundials are doing because, let's face it, we've all got perfectly good quartz, oscillating bits of quartz in our watches that actually keep time pretty much perfectly for us. So, yeah, it's not a problem anymore. And of course, bear in mind as well that even in a small nation like the UK, a sundial out in Cornwall, for example, would be given a different time to a sundial, say, over, in East Anglia. So, yeah. Anyway, there we are. Of course, as you probably know, a lot of people know this story. We use the same time everywhere, even our time zone in Britain, as a result of the development of the railways in the 19th century.
Yeah.
Because if everybody ran their own local time, and they did before that, then, of course, train timetables would have been impossible.
I was trying to explain this business that Britain used to have local time zones to my daughter recently. She thought I was quite mad. She refused to believe a word of it, but there we are. Rachel, I think we had a comment there that perhaps you might like to read out.
All right.
Yeah, there was one just then from Ian saying it's interesting to note that the whole of the system of units are based on 1 second of time, which he believes is ascertained from, can't even read numbers, average by the dead. And you can see it, Keith. I'm guessing it's directed at you, but there was also a comment if Lou wants to pick up from before we move on as well.
Yeah, of course, he's absolutely right in his next comment that, of course, we set our watches, our mechanical devices in relation to natural phenomena in the first place. Of course, as a lot of people know, the System International set of units, there are 7 base units, which are defined by experiment, if you like. And basically, the second is one of those base units. Of course, it isn't defined that way anymore, that you can see in the commentary. It's done by atomic oscillations, if I remember correctly.
Cesium atom
nevertheless,
oscillations.
Yeah. And the other thing, I mean, a lot of people don't realize this, that the meter, the length, 1 meter, was originally defined as 100 millionths of the distance between the pole and the equator. It's 100 million meters between the equator and the pole, assuming the Earth is a perfect sphere, of course.
Oh, really? Interesting.
You know it's flat. There was a question for Lou. It says from City Space Astro, it says, "Great, Lou. The images are amazing. What is the smallest exoplanet image so far? And do you think JWST, James Webb Space Telescope, will be able to image exoplanets directly?"
Right. So this kind of flies in the face of everything I just said. The smallest planet image so far, I believe, is about 1/10 of a Jovian mass. And this planet orbits Alpha Centauri. Okay, so now we don't have a very large planet reflecting a lot of light, but we have a star that's a lot closer, right? 4.2, 4.3 light years just across the street in cosmic terms. JWST should have the spatial resolution, I think, to be able to image a number of exoplanets. And of course, as we found out in previous weeks, some of its exoplanet identifications are going to come from spectroscopy of the atmospheres of those planets.
Absolutely.
Oh, thanks for that, Lou. Thanks for that.
Well,
sorry.
I hope that answers your question. And moving on. Steve, have you got anything for us this week?
Well, nothing direct other than, well, a couple of musings actually about related to what Kevin was saying. That it's interesting that I think back in the old days, people used to fall into an interest in astronomy simply because the skies were more evident above them with less light pollution. It's so much more difficult now because most people are in urban areas of some kind with very few stars to see. But the other thing I was going to mention is that I've just today come back from an astronomy field trip that I organised for Macclesfield Astronomical Society, MacAstro, over on Anglesey. We go out there half a dozen times a year, and at this time we go for the Perseids, which you probably will have realised, those who've been looking out for them, were considerably washed out by the full moon this year, but we still did see a few. But the particular highlight, certainly for me, was on the Sunday evening. We were out there just scanning around generally. I was looking direct at Arcturus, just looking at what a noticeably orange colour it was. And I then saw a satellite trail just to its left, just for literally a few degrees, 2 or 3 degrees, a bit like the old iridium flares. It just became evident and then faded away again over a period of about 4 or 5 seconds. And I thought that was interesting. And then about 5 seconds later, two others appeared directly parallel on exactly the same track to the left of Arcturus. And I suddenly realized what was going on. It must be Starlink. I didn't know a Starlink had been launched at that stage, but we found that out subsequently. And we watched these things over 10 or 12 minutes, saw about 35 of them. I understand that 46 were launched. And they just wended that. They started off slightly to the left of Arcturus and just gently moved, the tracks just gently moved across to the right of Arcturus over this period of about 10 minutes. But it was quite fascinating. And what really baffled me was why they were only visible. They kind of faded into and out of view over this incredibly short band in the sky. We didn't see them trailing anywhere else across the sky at all. And that really puzzled me, because it couldn't have been just straight reflection from the sun, because that was only not far over the horizon. I think that would have been evident for much longer had they just dipped into the Earth's shadow, and that being the reason. So it's a bit puzzling as to whether it was the solar arrays unfolding or the propulsion being evident as they left the carrier. Really don't know, but if anybody does, I'd be really pleased to find out.
Well, you can check the Heavens Above app, which will tell you, that will confirm that it was Starlink. So it'll tell you when they're visible. And I've got that for my phone, and it's wonderful. I wouldn't be without it for satellite spotting and tracking. It's quite amazing.
Yeah,
we had a shooting star event, and our guests, as I was showing somebody, I think we were looking at Saturn or something else, the guests had said, hey, we keep seeing the same, it keeps coming past, and then another one, and then another one, and they saw the same thing, and they picked that up. But it was a very short window. It wasn't, they did fade out quite quick.
Yeah, very puzzling.
But when I saw them
fascinating event. Fascinating.
When I saw them from here, I saw them rise up from the western horizon. And they went over. I couldn't see because my view was blocked by the house, but they definitely went down behind the house, and they were visible for a good few minutes. As they crossed, 66 of them it was on that launch as well, crossing the sky one after another.
Yeah, I've heard a number of reports of the Starlink streams, as it were.
Yeah, that was what it was.
Parallel. But this was really quite different. It's quite odd to figure out what was going on.
Perhaps we can find a solution to that, Steve. Perhaps somebody will know why that is. Okay, I'd just like to carry on with what I was talking about last week, really, which is the fact that the James Webb Space Telescope is very much in the news. But in fact, over the next decade, we've got a whole new generation of telescopes, both on the Earth and in space. And I'd just like to tell you about another one of them. So perhaps, Daz, if you could, there's a video in this, so perhaps, Daz, if you could...
okay, then I'll sort you out.
If you could make me the host with the most.
There you
Okay.
go. It should be...
Okay, just give me 1 second. Hope you can all see that. It should say 2027.
Yep, it does.
Okay, so coming up in 2027, we have got, believe it or not, the European Extremely Large Telescope, or ELT, the biggest optical telescope ever built. This is a huge observatory being built in Chile. And it is an optical and near-infrared telescope. Believe it or not, its optical system is based on that of an owl. No, if you believe that, you believe anything, of course. I put the owl up there because the ELT is based on an earlier design of telescope, which was bigger, which was known as the Overwhelmingly Large Telescope, or owl. So I just sort of put an owl there. And the owl originally had a 42-meter mirror, and they realized that if they shaved off the outer ring of mirror segments, they could save €1 billion. And that cut it down to a 39-meter mirror. Because, of course, it's not just the mirror segments, it's all the support for the mirrors and all the other technology makes everything heavier. So they shaved the outer ring of mirror segments off and saved €1 billion, and it became a 39-meter telescope. It's situated in Chile, not far from the European Southern Observatory's parallel observatory that we mentioned earlier. It has a 39-meter mirror, and if you compare it to Big Ben, this is how big the building is going to be. As you can see, it's what's the word for that? Monstrous, I suppose. Absolutely.
Humongous.
Yeah, humongous. That's a good description of it. Humongous observatory. This is its mirror compared to the size of the James Webb mirror. And the Hubble mirror. So you can see the three sizes of mirror there. The Hubble telescope at 2.4 meters, the Webb at 6.5, and then the ELT at 39 meters. And it does say 2024 there for completion, but of course it's been delayed by COVID, and it should be complete in 2027. It should see first light in 2027. Now, it is an optical near-infrared telescope. It's got these adaptive optics. If you look at the picture on the left, those are the 8 laser beams, and they are incredibly powerful lasers with this telescope. They create an artificial star in the sky because right up in the atmosphere, there's a layer of sodium atoms that fluoresce when you strike them with laser light. And that creates a sort of an artificial star in the sky. Now, by measuring the atmospheric turbulence, by observing that artificial star, the twinkling, if you like, of that artificial star, you can then use what's called a deformable mirror to counteract that exact turbulence, cancelling it out altogether. And by doing that, you can produce rock-steady images of stars in the sky without the twinkling that we're used to seeing. And this is called adaptive optics. So this will mean that the telescope will be capable of producing images of 15 times the resolution of the Hubble Space Telescope. So again, as we've said before, the Hubble Space Telescope is nearing the end of its life, but it's outliving its usefulness because the latest generation of ground-based observatories will far exceed it in certainly resolution. Main mirror 39 meters. That's made up of that composes 978 square meters of observing surface, and that is made up of 798 hexagonal mirrors. 798, so a lot of work there, obviously. And where those mirrors join together, obviously they have to be perfectly level with each other to form the surface, and they have to be joined together with an accuracy of 10,000th the width of a human hair over the whole surface of the mirror. So this is the accuracy that has to be attained. Otherwise, the telescope will produce blurred images, which is quite a tolerance, I think you'll agree. The field of view of the telescope will be 10 arc minutes, and it's going to tackle some of the biggest scientific questions of our time. So, tracking down Earth-like planets around other stars in the habitable zones where life could exist, probing the nature of dark matter and dark energy, the study of stars in our galaxy and beyond, black holes, and the evolution of the first galaxies. And of course, we should always expect the unexpected, because who knows what other wonderful stuff it's going to discover that we knew nothing about. So that is the future. And here's a short video about showing you the telescope. So there you have it, the extremely large telescope. I think you'll agree. Yes, Daz.
From the chat, Andy Weller asks, wonder how many distraction spikes we'll have with this one. Also, City Space Astro says, Andy, given that we know from space telescopes what a star should actually look like, why use lasers for a control star?
Well, the way that it works is that what you're trying to measure is the amount of turbulence in the atmosphere, the movement of the atmosphere that causes twinkling. So you're not trying to measure the amount, you're trying to measure the characteristics of that twinkling, how the air is moving, how fast it's moving, what direction. And by creating that artificial star, the light from that star bounces off the sodium straight back down to the telescope, where it's received and converted into a waveform. And then what you need to do, you create another waveform, which is the exact opposite of that, feed that to a deformable mirror. And when the light comes from the telescope, you feed that light through that deformable mirror, which is moving exactly the opposite way to the turbulence, and it cancels the turbulence out. This all happens very fast, of course. Ultra fast computers process this information in real time, so that the light received from the telescope doesn't exhibit any twinkling at all. As far as the light is concerned, it's come from a perfectly calm atmosphere. I hope that answers your question.
Oh, thanks for that. And Ian McIntyre said it looks like the Death Star.
Well, I'll tell you what it reminded me of, Ian. That view inside it is, I think you'd agree, is absolutely stunning. It's like an enormous cathedral of astronomy. It's got that sort of power to it, being inside a building like that. To me, it's reminiscent of a cathedral. Yes, Lou.
I wanted to show just one quick slide here, since we're talking about it. This is a comparison of pictures of Io. The two images on the left are from the Keck Observatory, the top one at 2.2 microns, the bottom at 3.5 microns. The upper right is the Galileo image, up close, very close, so it gets great spatial resolution. And in the lower right, you see the image of Io without adaptive optics. The two images on the left from the Keck Observatory are using adaptive optics. So you can see what a difference it makes.
Fantastic.
So it's a huge difference. It does make a huge difference to the seeing, because we've got to remember, looking up through our atmosphere is like a frog looking up through a pond, seeing the sky. We've got this thick soup above us that's always moving, or most of the time is moving. And adaptive optics allow us to counteract that movement of the atmosphere. And the adaptive optics system on the ELT is the most advanced ever built. And this is what's going to enable it to produce those images 15 times the resolution of Hubble. So we look forward to that. Quite an amazing instrument. Oh, there's just hang on, just give me 1 second, because I want to just put up very quickly one image that I did forget. The latest photo of it, the latest photo I could see is this one from January. This was the construction site in January this year. As you can see, it's high up in the Atacama Desert in Chile. But as you can see, construction is fairly well advanced. They got the foundations in, I think, and they're starting to build the walls of the observatory. And of course, they had to do all the preparatory work. They had to put a road in, obviously, for construction traffic and for anybody coming to the site. But that was what the Extremely Large Telescope looked like in January this year. I don't think they've released any photos since. So it'll be interesting to see what it looks like now. And it is on target for 2027, and it is within budget. So this is, don't forget, this is, again, an international collaboration between all the member states of the European Southern Observatory. So a truly international collaboration, and I'm sure it's going to make some amazing discoveries.
And it's interesting how they fitted it in a Iron Age hill fort.
Yeah, well, they had to blow the top off this mountain. There's a video of it somewhere on YouTube. They had to blow the top off to flatten the top of this mountain.
Yeah.
But you know, we know the Atacama Desert is probably the driest, apart from Antarctica, probably the driest place in the world. There are some places it hasn't rained for 100 years. So you know, they're guaranteed good seeing there. So,
that must have been a problem for it, because every gallon of water they've used to make the concrete has had to be brought in.
yeah, absolutely. Everything
Yeah.
has to be brought in. Yeah, because
And the setting time of the concrete in such arid conditions will have to be adjusted. Every constructional method has to be rethought in those extreme circumstances. It's incredible what they achieve.
it is. It is very clever people. There we are then.
Right, before we go, Andy, it's been mentioned a couple of times, but I think we've got to have at least one web image. So
Certainly.
if I can just share my screen.
What's
and
new
if you
with web?
remember a few months back, there was a big furore about the Hubble Space Telescope. You're in my way again. The Hubble Space Telescope imaging the most historic star that it has ever seen, and it was called Arendelle.
Yes.
Which means rising star, or I think it's morning star. Yeah, morning star or rising light. Now, this image here is a James Webb Telescope image, and it's another deep field, and it's actually caught Arendelle. Now, if you look here, on that, sorry, it's small, but there's a small round circle. Now, if I move this on, that is Arendelle in the middle. And as we know, going like we were speaking about last week, about gravitational lensing, I'll just pop back to the original one just to show you. This is a galaxy that has been lensed, and it was amazing that the Hubble was able to pick out just one single star from that galaxy. And of course, now it's been imaged by James Webb. And as you can see, you've got the lensed galaxy, a nice little curvature there. And then if we just sort of come over here, that is it there. That is the earliest star we have ever seen.
Isn't that amazing?
And that's imaged by JWST. So I just thought I'd pop that in. It's been mentioned all night, but we didn't get any.
So the other two in that image along the arc of the lens, are they in the same galaxy, or are they foreground objects?
I'm not sure, but if you look at them, they're almost identical.
They
I'm
are,
just
aren't they?
wondering whether it's a mirrored image.
I was going to say, could it be a
something else in
multiple image like the ones we were talking about last
Yeah.
week? Yeah, very
Well,
interesting, guys. Thank you so
okay,
much.
That's all right, no problem at all.
Right then, well, I'd like to say a big thank you to Kevin for joining us this evening.
Yes, thank you,
Kevin, you're
Kevin.
always welcome. If you want to drop in, you're always welcome, mate. So it's been lovely to meet you, and we hope you'll come back and see us soon. And good luck with all your observing. Clear skies, of course, as ever. And you're on mute, by the way, Kevin. So been lovely having you here, and we wish you the best of luck, and keep those photos coming into us.
Yeah, thanks, Andy. Appreciate it.
My pleasure. Thanks for being here.
And you've got a lot to look forward to with the sun, because it's still ramping up. So
Still ramping up.
Indeed.
Yeah. And good luck to all of you astrophotographers, and may you have clear skies. And that's about it from us for this evening. We'll be back next week, of course, with more chat and stuff to educate you and entertain you, or whatever. And thank you for being here. We do appreciate it. Don't forget to like and subscribe if you will be so good. It really does help us. A couple of clicks go a long way. And we'd like to wish you a very happy week. And we will all see you same time, 8 o'clock UK time next week here on Space Oddities. So goodbye from everybody.
thank you.
Good night.
Bye. Hit
Bye.
those likes.
Right, that's a wrap.